All right, so several meetings ago, probably this summer, we talked about this book, Laws of the Game, by Manfred Eigen and Winkler. And this is a book that talks about game theory in biochemistry and physics, and it talks a little bit about their application for on like cellular automata or in computation. So Manfred Eigen, of course, was the pioneer of things like the hypercycle, but he also had this interest in game theory where you can play these games that mimic things in biochemistry or in physics, and they can have you can have these different strategies for playing them and all of that. And so in this book, one of the types of games he talks about are these bead games, where you have beads on lattices. Like we talked about in the meeting, these lattice methods that people use for modeling, and you can model different types of scenarios on that kind of board. So it's not quite like the game Go, but it's a similar principle. And so I think it was Hussein who mentioned that chess is a stupid way to think about game theory, and maybe these kind of bead games are more appropriate for things like biochemistry, which I tend to agree with because again, chess is a specific type of strategy, and these bead games are much more useful for things like biochemistry, especially when you have competition and you have different types of processes, dynamical processes you want to understand and replicate. So the other reason I bring this up is because I found this website. This is David Ellerman, and I guess he's some sort of polymath. He does a lot of stuff with like economics and other types of law applications. And he also does like quantum mechanics and mathematics. And he has this set of Excel spreadsheets, which are a little bit archaic way to do this, but he's modeled some of the games and the laws of the game in these spreadsheets. And I wanted to look at these spreadsheets and go over some of the games that he's taken out of the book. So the book itself is, proposes these bead games. It proposes different types of strategies for playing them. And then he's taken some of those things out of the book and run some simulations and spreadsheets. So one of the things he talks about is the Ehrenfest-Earn model. And this has there are a couple of versions of this. This is with the random initial state. So if you go to the book and you look up Ehrenfest-Earn model, you'll find that, and this is a screenshot of the spreadsheet. So I have the spreadsheet in sort of Google Sheets now. And but this just shows the structure and how this is calculated. So there are equations in these cells, and you can have an input matrix here, find the sums, and then this just shows the distribution or the ensemble that you get. So a couple of notes on this: the initial distributions of zeros and ones is random. So basically, we have this matrix of zeros and ones that come from these inputs on each axis, and then you have the sums down here, and then you have zeros represented by an empty cell and ones represented by these black boxes. And so you have this distribution of black boxes as a sort of ensemble that is the result of this random initial condition. So the initial distributions of zeros and ones is random, and then you play the game and you get this, mixing that occurs. So you get this random distribution of zeros and ones, as you can see. Each iteration in a cell in the 16 by 16 array, which is the size of our grid here, is randomly selected. The entries can be 0 or 1. When a cell is selected, its entry flips to the other value. Since the most populous value tends to be selected and flipped, it is negative feedback. The equilibrium towards which it tends to is where you have 256 divided by 2 equals 128. So, in other words, like half of the cells will be zeros, half of the zeros will be one, and that should happen over time. So, what you have here is you have this initial distribution, which is random in nature. These black squares are randomly distributed. Then we randomly select cells and we flip the values. And we keep doing this over time as we select cells. And then if, what happens is that the most populous values tend to get selected and flipped. So when the most populous values get flipped, it's negative feedback, which reinforces order. And so this is a nice sort of way to show how order can emerge from randomness. This is the Ehrenfest urn where we have a uniform initial condition, or where we have an all black initial state. And so again, we have an initial state that's all black, and then we play the game and we get to the point here where this array occurs. And so initially each cell is black, each ball in our... So what we're doing with our random process, the reason they call it an urn, is because there's this whole class of problems in statistics called urn problems. So you have different urn models proposed by different people. You can model different types of sampling in this way. So you have this urn, which is like a black box, and you have a bunch of balls in the urn. And the idea is you reach into the urn and you pull out a ball. It's either black or white, in this case 0 or 1. And you don't see what you're pulling out, so it's a blind process, blind with respect to selection. And you're pulling out a ball and you're putting it on the table. So the idea is if you reach into the urn enough times and you pull out balls, the distribution you'll get is random in nature, and you should get a random distribution. That's the idea. Now, in this case, so in the last case, that was a random initial distribution. We're drawing balls out. We have an equal number of zeros and ones, and we're just drawing them out at random and placing them on the board. In this case, we have a uniform initial condition, which is that every ball in that urn is black, and so when we reach out and we put something on the board, it's always a black ball, and all of our cells then have black balls in them. And then once we populate our grid, then we evolve our grid. So each iteration in a cell in the 16 by 16 array, so we have 256 spots, is randomly selected. So the entries can be 0 or 1. So we start all with a uniform state, and then we start to iterate on that by flipping the values to things that are not black balls. When a cell is selected, its entry flips to the other value, so we select something, it flips. And this happens over a number of iterations. Since the most populous value tends to get selected and flipped, again, it is negative feedback. And so then our equilibrium tends over time to be where we have half of our grid being white balls and half being black balls. And we end up in the same place that we do with the first example, where I showed you that it was a random initial condition. In this case, it's a uniform initial condition, and because of the way the game was played, we end up in the same place. Okay, this is the bead game, which was from page 52 in Laws of the Game. So this is selection. So this is where we have our 1,000 iterations of this game. We have this lookup table where we have this set of 1s and 3s. And so this is an 8 by 8 matrix. And then now we have our relative changes here over 1,000 iterations. So in this game, on each iteration, a square is randomly selected. The value is doubled, and its content is then assigned to the second randomly selected square. There are 4 possible contents, 0, 1, 2, and 3. So what happens here is we have any one of these values can be 0, 1, 2, or 3. In this case, we have 1s and 3s only. And each of these are represented by, this is from a deck of cards where you have clubs, diamonds, hearts, and spades. And then, each state from 0 to 3 is represented by one of these symbols. So you can get a sense of what the contents are by that. So you have this ensemble with different distributions of these symbols. On the first iteration, the contents of the squares are randomly assigned. Eventually, one suit will tend to dominate. So the idea here is that we again have this case where we randomly distribute these symbols. We can use an earn model to draw out, we can have a number of these symbols evenly distributed. We can place them on the board, but over time, as this game progresses, you end up with one symbol that predominates the board. And so in this case, I don't think that's the case in this iteration, but for later iterations, say like for example, we look at this, we have all four symbols evenly represented on the board. We keep playing the game as we see here in the rules, and then we end up over time with enough iterations getting a single symbol that predominates. So you might have most of the board filled with hearts, or all of the board filled with hearts. So eventually one suit will tend to dominate. One can keep score by watching the relative changes relative to an initial random assignment. So you can actually score this and see the dynamics of this change. Okay, so that's that's the bead game in selection. This is going back to the Ehrenfest model with cooperative phenomena instead of what we showed before with an initial condition. This is where we have this matrix, and we have 600 iterations. We have a matrix of zeros and ones with the sum down here, how many ones you have in each row, or in each column. We have our neighborhood sums here, and then we have our board where we have red squares and blanks. And so that's what our board looks like. It looks different than the other boards. And why is that? So let's take a look at the instructions. So the entries in the 16 by 16 array can be 0, blank, or 1 red, these red squares. In each iteration, the entry in a cell flips to the other value with a probability of proportional to the number of 8 neighbors equal to the other value. So in this case, we have these neighborhoods of 8 cells surrounding an initial cell. So this cell here is going to have 8 neighbors. It's going to be every cell that surrounds it. 6 on the top, 6 on the bottom, and 2 on each side. That neighborhood of 9 cells then will shift. So, this cell will have a neighborhood of 8 neighbors. And this cell will have a neighborhood of 8 neighbors. And this cell will now be a neighbor of this cell. So you can see the parallelism where you move across the board. And each cell can either be sort of in the middle of a neighborhood or in multiple neighborhoods. And so that's what they mean when they talk about neighbors. And so we also see up here where we talk about our neighborhood sums, we have our neighborhoods defined and the sum within that neighborhood. So what we're going to do is we're going to start with our 16 by 16 array. We're going to have multiple initial starting points. We're going to flip the entries in a cell to some other value with a probability proportion to the number of the 8 neighbors equal to the other value. So when we have a majority of cells that are blank, that central cell will then become blank. This is very similar to what we do in cellular automata in neighborhoods, in more neighborhoods. And so then the initial distribution of zeros and ones is random. So we can have an initial distribution that's random. We can have this update rule, and we can end up with, this sort of order that emerges. A higher stabilizer value makes it harder to flip a cell's value. So we can have stabilizer values that can change the dynamics of this game and make it harder to actually flip cells. Because sometimes there's this tendency in, for clusters of blank areas to be reinforced through this kind of a process. Sometimes it's easy for the whole simulation to converge on one state or another through this process, but there's stabilizer values that we can use as well. Okay, that's just for this instructions. Okay. This model was motivated by the description given on pages 71 to 72 in Laws of the Game. So if you're interested in following up on this and playing with the spreadsheets, they have this set of Eigen sheets. So this is kind of like for these different parts of Laws of the Game. So we have board game, bead game equilibrium. This is where you have an all black starting state. Bead game equilibrium, we have a random start. There is this bead game once and for all, and I didn't talk about that yet. And so the once and for all game is a variation on these games, the bead game, but it has a distinct strategy. And that strategy is to try to have like kind of a solution that is a winning strategy. So in other words, the dynamics of a lot of the games in these, the dynamics of a lot of these bead games tend to lead you to sort of some sort of equilibrium state. It isn't necessarily where you have a game where you have all one state or all the other state. They tend to fluctuate with different internal patterns. But in once and for all, the goal of the game, the object of the game, is to dominate everything, to finish off your opponent, and to become the dominant state. And so, once and for all is sort of a way to model small-scale catastrophes. These kind of takeovers of one state or another is a small-scale catastrophe. And what I mean by small-scale catastrophe is to go to Renee Tom's catastrophe theory and think about how catastrophes operate. In other words, you have these sort of large-scale changes that occur that reorder a system. And that's kind of what you want to do with this once and for all strategy. And so the idea is that you have this, basically this internal mechanism in the game, or these strategies that play upon fluctuations in the dynamics of the game. So as there are changes happening within our matrix, we try to seize on those fluctuations and amplify them. And so there's an internal mechanism within this game strategy that's employed that responds to fluctuations in an exaggerated manner. So that means that, in terms of responding to these fluctuations, you put a lot of resources into sort of dominating the game. And so through these kinds of strategies, we can actually examine these games and look at the precursors of homogeneous states. So, if we see this in a system, if we see a catastrophe, like where we see an extinction of a species in a food web, we can actually go back and look at what the precursors were. What were the sort of dynamics of competition that led up to this problem? Or maybe there was an external perturbation. So what was, maybe that external perturbation didn't do the job by itself. Maybe there were other dynamics within the competition structure of that food web that led to that extinction event. And so once and for all allows us to look at those kinds of dynamics. And so once again, if you're interested in downloading these Eigen sheets, you have the bead game, and you have different versions of the bead game, and then you have the Ehrenfest model with cooperative effects. And those all kind of point to different pages in the book. And then finally, if you're interested in some of the other things that he's done, you have Kaufman sheets. So he's also done this for the book At Home in the Universe by Stuart Kaufman. These are modeling the Boolean networks and fitness landscapes that Kaufman talks about in that book. He's also implemented simple genetic algorithms, and then, the game of life, different iteration counters, looking at the glider gun within the game of life. He's done some epidemic modeling, some simple genetic algorithms here from John Holland's book, The Hidden Order. And then, of course, Polya's City. So I talked about Polya's Urn, or I talked about Urn models. And Polya's Urn is a version of an Urn model where we do sampling with replacement. In other words, we put a bunch of balls in the urn, and then we sample balls out of the urn. And as we sample balls and put them on the table, we get new balls in its place, and it's according to the original distribution of balls in the urn. So we're always drawing from a fixed probability. And so we can use these kinds of things in Bayesian modeling, where we have this process where we're gaining information and we can adjust the probability of that urn. We can replace the number of balls in that urn. So we have a continuous sort of distribution, and we can model things fluidly like that. And so this just kind of goes through Polia's urn and talks about sampling with replacement and how that works on a grid. So he plays this out on a grid. So Polia's city is a circle or ring of neighborhoods. When a location hits 0, it goes broke. To the neighborhood effect, a location that has gone broke can again go positive if it has a non-zero neighbor, and then it is possible for the next broke neighbor to go positive, and so forth. Okay, so this is basically where you have these grids with sampling with replacement, and you get this structure across space, and he calls it Polia's city. Very interesting stuff.